Okay, so welcome back. I would like to continue with where Johannes left off last time. So if you recall, we are, just as a reminder, what are we trying to do? So we have this error parameter that we call lambda, and it is by definition it is a difference, so it is the maximum of these errors. So we are trying to prove that this green function gij is close to the identity times m, where m was this Stieltjes transform of the semicircle law. And so this, I recall, is an object that depends on z, so everything depends on z. And z lies in this spectral domain S, which was a rectangle in the complex upper half plane. And this is also random, so it's a random object. And we are trying to prove proposition 20, which says that so in S, so for Z, so this is a z-dependent function. This also depends on z. I recall eta is the imaginary part of z. This is our notation, so it's a function of z. And this was the stochastic domination. So we are trying to prove this. This is an important, one of the main results in this section. This is the so-called weak local law. It's weak because this error bound is not optimal, but nevertheless it's an important result in the proof of the full local law. So you started proving, started the proof last time with Johannes, and you did this lemma 23, I think it was. You concluded that one, right? You should correct me if I'm wrong. And that contains the main estimate. So if you recall, we have the basic philosophy in deriving this kind of thing. There are two big steps. One is to use the Schur complement formula to derive a so-called self-consistent equation for the entries of this G. And this involves lots of error terms, random error terms, which were estimated last time in this lemma 23. And if you recall the estimates, they always take, there are two possible starting points for the estimate. One is that the imaginary part is sufficiently large, bigger than or equal to 1. And then doing these estimates is going to be easy. And the reason for that is that the entries of gij are bounded by 1. Right? This is something you saw. I mean, this is a sort of an obvious fact. You saw it in the first problem set. If you have a resolvent or green function, and if the imaginary part of the spectral parameter is at least 1, then the G, if you recall G in operator norm, bounded by 1 over eta, therefore the entries are bounded by 1 over eta. If eta is at least 1, then these entries are all bounded by 1. And the other the other hypothesis under which we will work is going to be the hypothesis that this function phi is equal to 1. And that's an important thing. This is a clean way of writing something that you will see is in fact an induction. It's a multi-scale induction on scales. It has many names, bootstrap argument or something. I'll explain it today. And if you recall, this was the indicator function that this thing is. I think it was tau over 10. The exact number doesn't really matter, it just has to be sufficiently small. So this says that this function is equal to 1 if this quantity lambda is small, not very small. I mean, this is a tiny exponent, so it's just a bit smaller than 1. That's how you should read it. And if you work, we will work on this assumption that phi is equal to 1. We're going to prove that if lambda is small in this weak sense, then in fact it's going to be very small. And this is kind of a bootstrapping that will allow us to perform the induction. We'll see how that goes today, but this was to recall these were the two assumptions that you had in this proposition 23. And under either of these, all of these error terms were estimated nicely by this parameter that we called psi theta. So let me now come to the new material. So you finished the proof of proposition 23, right? I think this was what we got to. And now let me give you another lemma. So this is another preliminary lemma, which has nothing to do with probability. It's a completely elementary lemma about solutions of quadratic equations. So you all know how to solve quadratic equations. So in principle, there's nothing deep or shocking about this, but you will see we will use it because the so-called self-consistent equation that rules our whole proof is a quadratic equation. It's a very simple quadratic equation in one complex variable, and we have to analyze its solutions well. So let's take a complex number in this set S. It doesn't really matter it's S. It can be any bounded set of the complex upper half plane. Then the equation so this is my equation. So it's an equation in one unknown variable u, which depends on the parameter z, and this has two solutions. Well, generically, if z has some particular values, then it has just one solution, but you can view these two solutions as coinciding in that case. Although if I assume z is in the open upper half plane, as I do here, then it has two distinct solutions. One, which I call m, and this is in the upper half plane. And we've already seen this, right? This was one of the characterizations of m, so it's the same m. It's the Ciottos transform of the semicircle law. And the other solution, it's a quadratic equation, so it generically has two solutions. And the other solution, now I have to also consider the other solution. And the other one, which lies in the lower half plane. Okay, I use a star for complex conjugate. The bar could be ambiguous, it could denote closure, but this is just the lower half plane. Okay, so it has one solution in the upper half plane, one solution in the lower half plane. Moreover, they satisfy so the distance between them is of that order. So it's bounded. I recall this. Do I need to recall this notation? We've used it already before. Is this notation clear to everyone? Or would someone like a reminder of this? If not, I will not remind you what it is. So I remind you what, so eta, these are definitions we use throughout the course. So kappa was the distance of the real part of z to the edges of the spectrum plus minus 2, and eta is the imaginary part of z. So this behaves in that way. So up to some constant which can depend only on the kappa, the implicit kappa in the definition of S, this holds. So they are separated. So these solutions, it's difficult to draw a complex, especially difficult to draw two complex functions of a complex variable. But you can imagine as you move around in the complex plane, you move your z in the complex plane, these two solutions will move around. And if you get very close to the spectral edges with z, then the two solutions will become very close. Otherwise, they are far away from each other. And then the next statement is the so-called stability of the self-consistent equation, which is one of the major topics in many, many arguments in random matrix theory. This is the simplest instance of such an argument. The question is, if I have a quadratic equation with some coefficients. If I change the coefficients a bit, what happens to the roots? Now, I think you've all seen in some class that solutions of polynomials are continuous in the coefficients. Right? This is a qualitative statement about topology. here we need something quantitative. So it's not enough to say, of course, as you vary z, these solutions are continuous, fine. We will introduce another error parameter. So we'll replace the 1 with the 1 plus r, which is an error. The question is, how do the solutions vary as you vary r? And we know it's continuous as r tends to 0. The solutions will tend to these two, but we have to know precisely, we need error bounds. That's very important. So everything has to be quantitative. So if U solves the equation so for some r, and let me assume so r is a complex number and it's bounded in absolute value by 1, then U is going to be close to, well, close to what? I don't really know. It's going to be close to that one or to that one. A priori, I don't know which one. So I will write it like this. So U minus M. This is going to be small, or it might not be. If this is not small, then the other one is going to be small. So one of these two is going to be small. And I can express that by taking their minimum. So this notation, this is minimum. I don't know if you've seen this notation. It's just a lattice theoretic notation. It states that real numbers form a lattice. So this wedge denotes minimum of these two numbers, and this is less than or equal to for some constant, some positive constant c that depends only on kappa in the definition of this, in the definition of S. Okay, and this is optimal. So I mean, it's not very hard to do these arguments, and it's also you can imagine it's not very hard to get optimal bounds, and up to the precise best possible constant, which we're not interested in. This dependence is optimal. So this is the best possible bound you can write. So this says, again, if you solve the quadratic equation which you perturb by a small r, this is how the solution behaves. So it's still close by and close with that error. So let me give you the proof. The proof, as I said, is, I mean, it's just solving quadratic equations, right? So there's nothing difficult. You could have done this maybe even in high school already. So take this equation, this one. Let me first prove the first statement. Take this equation and solve it. Well, you use the usual formula for solving quadratic equation, and you get the formula which we already know. So this is also. Now, there's only one thing that's a bit tricky in this argument, is that you have to deal with square roots of complex numbers. And that's the only thing that makes it a bit difficult. And I'm using the convention, or the definition of the square root from Lemma 8, which means this square root, by definition, has a branch cut on the line minus 2, 2. Okay, so that's the definition of this square root. So then the plus, this is a uniquely defined square root. It has a clear sign. And I really take the plus. And the other solution, of course, is the same one with the minus. And I always use the same convention for the square root. So the first observation is we know already that M, because M is the Stieltjes transform of a probability measure, we know that this guy has positive imaginary part. Right? This we know from Lemma 8. This has negative imaginary part, right? Minus Z has negative imaginary part. That means that the square root must have positive imaginary part. Okay? If this whole number is to have positive imaginary part, this one needs to have positive imaginary part. Therefore, if you take this with a minus sign, this is clearly going to have a negative imaginary part. Okay, so this is the proof already that this is in the upper half plane and that's in the lower half plane. Okay, was this all right? I will not write up anything more about this argument. I will now, so I mean this is in. Then I need to verify this, but this is easy. So if I take their difference, I get right. So the absolute value of the square root is equal to the square root of the absolute value. That's true for any square root, any complex square root. And I can write this as and now because Z is bounded, it's easy to check that this is precisely of the order of the distance, the square root of the distance of Z to either of the 2 points plus minus 2. And that's precisely kappa plus eta. Kappa plus eta is in fact the L1 distance to the nearest edge point, plus minus 2. Okay. So next, so this was the claim about m and m tilde. Now I have to analyze this approximate quadratic equation. So if U solves so if it solved this quadratic equation with some r, then, well, I can also solve this quadratic equation, of course. So then I find that U is one of the two solutions of this quadratic equation, which I denote by mr and mr tilde. And this is so these are the two solutions of this quadratic equation, so that's a triviality. And here, now you may worry, well, what square root do I take here? And the answer is I don't care. So it doesn't matter which square root I take. You can take a really weird branch. It doesn't matter. They differ by a sign, and I pick up. If I change the choice, then I will just change which of these two I'm talking about. But all of the statements that I make, for example, this one is symmetric in terms of m and m tilde r, so the choice of the square root doesn't matter. You see the final statement also is completely symmetric in I mean here I take the minimum of these two. So I'm just saying I'm close to one of the two roots. I have no idea which. And this, in fact, will be an issue in the proof, is to make sure that we are really close to that guy and not close to that guy. But this elementary argument just tells you are close to one of the two roots. And now the claim that this is the claim follows immediately from a basic estimate about the complex square root function, which I will let you work out as an exercise. So this is going to be an exercise, and it's the following. So take any two complex numbers, w and zeta, so I would like to analyze the difference. So you take any complex square root, and any two complex numbers w and zeta. And I would like to estimate this difference. Now, of course, I always have the problem that as I said, I take any square root, so this is not in general not going to be small in any way if I happen to cross a branch cut, for example. Even if zeta is very small, if I happen to cross a branch cut, then this will not be small. So I have to take the minimum of these two things with up to any possible sign, plus minus sign. So this minimum is going to be small. This is just telling me that I choose the version of the square root of the two possible branches of the square root, which is the closest, which is the best possible choice for this estimate. And this is bounded by the absolute value of zeta divided by the absolute value of w, and then the minimum of so whichever is smallest, either the absolute value of zeta divided by the square root of the absolute value of w, or just the square root of the absolute value of zeta. So for any choice of the complex square root, and so this is, I leave as an exercise, first of all, to prove this. There are various ways of proving it. So in principle, it's a totally elementary fact about complex numbers. So you may think it's sort of obvious, but I think if you want to do it right, it requires maybe a bit some thought. And I also leave it as a small, easy exercise to figure out once you have this, how do you get that? Right? I mean, you just have to choose. You have to realize what should I pick what should I pick w to be, and what should I pick zeta to be. But it's basically given by, you can read it off these expressions. Okay, so the end of that proof will be left as an exercise, as I said. But if you do that, and all there is to do really is to work out this estimate. And if you do that, you will get, you get this estimate here. Okay. So this is a basic stability result that's very useful that we will use throughout the proof. And this is a prototype for a huge family of stability results that pop up basically anytime you try to analyze a random matrix model. In general, they can be much more complicated than this. They are often vector valued, or they can be vector valued, but in this case, this is just a simple quadratic equation, one complex variable. Okay, is this all right? Are there any questions so far? Okay, so this is the end of these preparations. So now let's come to the actual proof. Now we come to the heart of what we have been doing. So after preparations, well, this is the end of the preparation. So now comes the heart of the proof. It's a rather nice argument, and it goes by many different names. Sometimes it's called the bootstrapping. So the origin behind, I mean, the bootstrapping is a general proof strategy used a lot in all of mathematics, mainly in analysis and probability. I mean, the idea is you have straps on your boots, and then maybe this is not so popular anymore today, but in the olden days people used to wear boots with straps on them, and the idea is that you take hold of your straps on your boots and you pull very hard and you pull yourself up by pulling just on your boots. So in real life this is extremely difficult. In fact, if you've studied physics, you may know that there are some basic issues with this kind of approach. You can pull as hard as you wish. It's going to be very difficult to take off and fly. But in mathematics we can do that, and we'll see how that works. It sounds crazy. You start from a conclusion which you use to deduce a hypothesis, and then from the hypothesis you deduce the conclusion, and you go round and round in circles, and it sounds as if you're pulling yourself up by your bootstraps, but of course it's not that, there's no loophole. I mean, you have to make sure this is formulated properly, and we'll do that. These kinds of arguments, if they have a more topological flavor, they're also called continuity arguments. And in this case, there's a probabilistic aspect which is important. So I'll call it a stochastic continuity argument. Stochastic continuity argument, or also there is, you will see it's an induction on scales. So if you remember, the imaginary part eta denotes the spectral scale. So it's going to be an induction in eta, where eta starts from large scales and then you go down to small scales. There are many, many arguments, mainly in probability and statistical mechanics, about such induction on scales or multi-scale arguments, where you go from one scale to another scale and then you propagate this using some kind of inductive argument. And this is basically what we do here as well. So these kinds of arguments also are called multi-scale arguments. Okay, so what is it? So we do an induction on eta. So we will have our complex plane. So here's 1. And we will choose an initial value, an initial imaginary part, which is, let's say, 1, or it can be larger than 1. It doesn't really matter. The difficulty is in reaching small ones. So our goal is to get down to n to the minus 1 plus tau, if you recall. And what you do is you prove something here, and then you propagate the information that you just proved to go to a slightly smaller eta. So this would be eta 1, and this would be eta 2. So we will construct a rather dense lattice of these etas coming down. If it were a normal continuity argument, you could just do it continuously on the line. However, you will see every time we do one step, we lose some probability. And we can only afford to lose so much probability. And if we did it in a continuous way, we would lose far too much probability, because there's an infinite number of steps. So we have to have a finite number of steps. It's descending from, let's say, is greater than or equal to 1. So this is global scale. If you recall the spectral scales, eta greater than or equal to 1, or eta equals 1, is the global scale. And it turns out we will do steps of size n to the minus 3. So it doesn't really matter what the step size is. It should be sufficiently large, and this is basically, this works fine. I mean, you could take n to the minus 10. That's also fine. N to the minus 1 would be a bit too big. So this would be eta. So this is where we stop when we reach eta k is equal to n to the minus 1 plus tau. So what is the basic scheme? What is this bootstrapping? Let me explain the skeleton of the argument. So the point is, you have a hypothesis, which I call hypothesis at k. So you are working, let's say you are working here. Maybe let me call it k minus 1, because that's what I do in the proof. So you have a hypothesis at eta k minus 1. And this hypothesis is precisely, so this of course I call zeta, so zk is going to be equal to E. So I never touch the E. The real part is always the same. This is an induction which happens at a fixed value of the real part. And the hypothesis is that this indicator function phi at z k minus 1 is equal to 1. That's going to be my hypothesis. And this, you can view this as it's small, but small in a weak sense. If you recall, the smallness requirement here was not particularly strong. And then we will prove with very high probability so these implications I write, they are not true deterministically. They will be true only with very high probability. I will get what I call a conclusion at k minus 1, which is that this guy is very small. In fact, we'll prove it's bounded by psi, by this. Well, let's say we'll prove it's by bounded. Well, we will see what it's bounded by, but it's going to be bounded by a quantity that is much smaller than this n, if you recall lambda. So phi. So this is a very weak bound. And we will prove that if you have such a weak bound, in fact, you get a much stronger bound automatically with very high probability. So that's going to be the conclusion. So the hypothesis is a weak bound. The conclusion is going to be a strong bound, by which I mean this is very small. And then from that one, we would like to make a jump. So the key observation is if you have a strong bound here, using the continuity of all quantities involved, you can get a weak bound here, basically by using Lipschitz continuity of lambda. So that's where continuity enters the game. Continuity is crucial, otherwise, of course, if your things are not continuous, then there's nothing, absolutely nothing you can deduce about what's going on here from what's going on here. And so from this one, we will deduce by using the fact that lambda is n squared Lipschitz. This we've seen was easy was a triviality basically. We will deduce the hypothesis at k. Okay, so again, if you have a strong bound here by Lipschitz continuity, you can get a bound here. You lose something, of course, but thanks to the continuity, because these steps are sufficiently small, that's important. That's why it's important to make these steps small enough. You lose something, but the something you lose is so little that you still can recover a weak bound. And it's maybe not so shocking, you see, the functions involved are n squared Lipschitz. We take steps of size n to the minus 3. So the error between lambda here and lambda there is of order 1 over n, which is much, much smaller than any of the notions I play around here, or you will see also here in this very small. So that means that the error you make from this one step is negligible, basically, compared to these error estimates. And that's why I still I keep such an estimate. So that's going to be the basic structure of the proof. Now, there's one important note. So why can't I make these steps very, very tiny? Well, I have an order n to the 3 steps. right? I go down from 1 to almost 0. The steps are of size n to the minus 3. So I have an order n to the 3 steps. At every step, this implication is not deterministically true. It's true only with very high probability. So at every step, I lose some probability. If you recall, the very high probability is that the error probability is bounded by n to the minus d, where d can be chosen to be as large as you wish. So that's okay, because I will get an n to the minus d, which is multiplied by an n to the 3 from the union bound, and that's still going to be very small. But you see, it's important that this is the number of steps is polynomial in n, with some bounded exponents. So the error probabilities are multiplied by the order n to the 3. Okay, so this is to give you an idea of where we are headed. That's going to be the main argument, and this will conclude the proof, which we will do. I think we won't quite have time to finish the whole proof today. We will conclude it next week. So, of course, you have to start somehow. You have to start here. So, if you want, you can view this as an induction, right? This is an induction. You assume this guy, and you deduce through this bootstrapping argument, you deduce that guy, and then you can go on. Of course, you have to start somehow. So this is the start. At the global scale, so that's the following result. Which now has to be an unconditional result. So I cannot make an assumption that I am on this event, that phi is equal to 1. So if the imaginary part eta is sufficiently large, then this thing is bounded, stochastically dominated by n to the minus 1/2, in fact. Okay, so if we are sufficiently high up, then this lambda is small, and then both the hypothesis and the conclusion at k is equal to 0 hold. So let's prove this. We have now all the ingredients to do that. It's basically going to be an application of, first of all, getting such a self-consistent equation and using these properties of quadratic equations we just saw. So let's see how this goes. So let me now fix for the following. I will not talk about eta anymore. Let me assume eta is greater than or equal to 1. So from this lemma that you saw last time, which was all these preliminary estimates, which was lemma 23. And I also need to recall that the Stieltjes transform M is bounded, which was in lemma 15. We get so if you recall this lambda star, so that was the maximum of the off-diagonal entries. And in lemma 23, we saw that if eta is greater than or equal to 1, and then this lambda star was bounded by what we called psi theta, but using the fact that the imaginary part of M, or M itself, is bounded, and eta is 1, this psi theta is obviously bounded by 1 over square root of n. Okay, so the off-diagonal elements are easy to estimate. The more tricky estimate, of course, is to prove that the diagonal elements are close to n. So it remains to estimate GII minus m. So how does one attack the diagonal elements? Well, one uses the Schur complement formula, which, if you recall, was in this lemma 21, I think. Yes, lemma 21 was an immediate consequence of the Schur complement formula. Which gives a characterization, an algebraic expression for GII in terms of various other quantities, some of which were error terms that we estimated in lemma 23. So maybe I will just remind you what this lemma. So the way we wrote, so this was lemma 21. The way we wrote it was GII, 1 over GII is equal to minus Z minus G plus YI. And YI we proved exactly as before. We know that YI, when eta is at least 1, is of order n to the minus 1/2. Now if I just multiply both sides by GII, using the fact that GII is bounded by 1, I will get the following thing. Okay, so this was lemma 21. Right, if I multiply both sides by GII and I bring these terms to the left, I get this equation. Okay. Now I would like to get, this is starting to look a bit like my quadratic equation for G, but not quite yet. And in order to get a quadratic equation, I average over I. So by averaging, I mean you take the sum over I, you divide by n. So I get 1. Of course, 1, nothing happens to 1. This GII becomes a little g, right? If you recall, little g was just the average of big GII. So I get g squared plus zg. And this, by union bound, remains the same thing. This is all uniform in I. And this is now precisely obtained the quadratic equation for G, which is exactly the quadratic equation I was discussing before. And I have a small error term here. So if this were 0, this would be precisely the defining equation for the Stieltjes transform M. And this calculation using the Schur complement formula also shows you in a nice way where the semicircle law comes from. It's from this equation here. This is, in my view, is the most transparent way of seeing the semicircle law from these random matrices. Okay, so let me now solve this quadratic equation. So we saw this lemma 24, which gives us information about the roots of this quadratic equation. So we know. So we would like to prove that G minus M is small. Unfortunately, we don't really have that. We know that G minus M or G minus M tilde is small. Small in what sense? If you recall, the thing on the right-hand side in the estimate of lemma 24 was if you look at the denominator was square root of kappa plus eta plus absolute value of r. Since eta is 1, this denominator is at least equal to 1, so I can just ignore it, and I get 10 to the minus 1/2. So this is what I get from lemma 24. Now what remains to be done, I'm almost done, right? So I've almost proved that G is close to M. I just have to make sure that it's really G that's close to M and not, that G is really close to M and not to M tilde. So there's a little extra argument one has to do. This is important, these kinds of arguments. We will face the same problem in this bootstrapping argument. In this case, this is easy to do, and I will let you think about it during the break. So we'll have a break now and continue in 15 minutes, and then I'll tell you, if you haven't figured it out by yourself, how to do this. Okay, so let's continue with this argument. So if you recall, we got to this point, we showed that G is close to either M or M tilde, and we would like to make sure it's really close to M. And the argument in this case, so in general this can be a difficult problem. In this case it's not, because we know that G is the Stieltjes transform of some probability measure, right? It's the Stieltjes transform of the empirical eigenvalue measure, so it has a positive imaginary part. M, we know, also has a positive imaginary part, and M tilde, we know, has a negative imaginary part. Now, this information alone is not quite enough, but if we manage to show that the imaginary part of M tilde is sufficiently negative, let's say it's bounded away from 0 by some constant which is bigger than this, then we know that this cannot possibly, G cannot possibly be close to M tilde with such an accuracy, and therefore it has to be close to that guy. Okay. So that's going to be the argument, and that's in fact easy to see. So if you recall, M tilde was this minus Z minus the square root, and the square root was chosen in such a way that this thing has positive imaginary part, minus Z, yes, minus Z. And now this number has imaginary part minus 1. And this has a negative imaginary part. That so this, the imaginary part of M tilde, is for sure less than or equal to minus 1/2. And the imaginary part of G is greater than or equal to 0. Therefore, we conclude that G minus M is close to M to the minus 1/2. Right? It cannot possibly be close to M tilde. So that's exactly what we wanted to prove. So we've proved now, we haven't quite finished yet, we've proved that G is close to M, but now we have to show that this is true not just for G, which is the average of big GII, it's true for every single GII individually. So I would like to estimate GII minus M, which by the triangle inequality I estimate by GII minus G plus G minus M. And if you recall, we had an estimate for GII minus G in this lemma 2.3 under the assumption eta is at least equal to 1. And this, so each of these terms is bounded by n to the minus 1/2. We just proved this is bounded by n to the minus 1/2. And this from lemma 23 is also proved bounded by n to the minus 1/2. Okay, so that's the end of the proof. So this was a relatively simple argument. We just had to use use this, it was basically playing with this quadratic equation. We're going to do the same thing in the induction. So let's now come to the conclusion of this whole section. So let's finish the proof of proposition 20. Proposition 20 was the main result of this section, which was this weak local law. So I will fix an E which is in the allowed region of the real parts, and I will define these ZKs as I had before. So, yes?
I think you mean tau minus 1, right?
Tau, yes, tau, thank you. Indeed. I hope I didn't make this mistake in other places. My Greek letters occasionally get a bit mixed up. But maybe I said it orally, maybe I was talking about kappa, but the number that determines the boundedness of the spectral region S is tau. Okay, and eta k is equal to 1 minus k n to the minus 3. Okay, so this is exactly the setup we had before. You start at eta 0, which is equal to 1, and then you go down in steps of n to the minus 3. So we will fix an epsilon, which is a positive exponent, and we need it to be sufficiently small compared to tau. So in the various steps of the proof, the one number that makes everything work is tau over 16. And I will also fix a d, which is going to be the exponent of n in these error probabilities. And remember, I would like to prove that in this proposition, I would like to prove that lambda is bounded by n eta to the minus 1/4. So let me define an error parameter, which is n eta to the minus 1/2, and I call this delta k. N eta k to the minus 1/2. And in order to formulate this bootstrapping argument carefully, I need to define two events which all depend on k. So for every k, I could write zk, but I just write the index k. So I have events and quantities which all depend on k through my zk. So all the arguments, when I'm at the position k, all the arguments z will be equal to zk. And this event is the event that theta, if you recall, theta was equal to g minus m. So this was the quantity we were estimating, for example, in this argument. So these are good events. So these are events which I would like to show hold with high probability. And this is precisely the error bound that I get from this lemma. What was it? Anyway, the lemma that gives me the solution of the quadratic equation. I will get from the analysis of this quadratic equation, I will show that this thing, theta, is with high probability stochastically dominated by such an object. And if I want this to hold with high probability, I have to add an n to the epsilon. And then I have another event which I call xi. This is xk, and this is just telling me that lambda is small. So it's bounded by square root of delta k. And again, if I want to prove that this holds with high probability, I need a small power of n, and it turns out here I should put the exponent 2 epsilon, you will see. I mean, the only way to figure out these exponents is to go through the proof and to check that they work in all steps. So these are the two events. So the first one says that theta is small, and the second one says that lambda is small. And we will now perform the bootstrapping, so it's a stochastic bootstrapping, which means that we are trying to establish these events with high probability inductively on K. So the first step is to prove that both events hold with high probability for K is equal to 0. This we just did. So by lemma 25, and of course, just by averaging, I always know that theta is less than or equal to lambda, right? If you write theta as the average of GII minus m, you see that if GII minus m is bounded by lambda, then theta is certainly bounded by lambda. So I proved, you see, if you now take eta equals 1, and so k is equal to 0. Let's start maybe with this one. If k is equal to 0, I get n to the minus 1/2. So here I have an n to the 2 epsilon times n to the minus 1/2, and I just proved that this event holds with very high probability, right? And the same thing here on the right-hand side. If I take eta k equals 1, I get n to the minus 1/2 times n to the epsilon. So in other words, I know that this event, omega 0, and the event C0, they both hold with very high probability. So with the union bound, I know that the intersection holds with high probability, which means that the complementary event has probability n to the minus d. Okay, so this is what we just did. This is just rewriting. I mean, if you're not used to these kinds of notations, it may take some time to juggle these statements in your mind to get something of this form. But that's nothing more than what we just proved. So now for the induction. We want to go from k minus 1 to k. So what we will assume, we will assume that these events hold. So we will assume that omega k minus 1, ck minus 1 hold, or in other words, we work on these events. And we will prove that on these events, the probability that omega k and ck hold is large. It's very high. So here the key difficulty is to ensure, as before, but now it's a bit more difficult, is to ensure that G is close to M. So in lemma 24. And in fact, there are two cases. In order to do that, I will draw a diagram which will make it clear. There really are two cases. It's not just because that's why we like to organize the proof or something. That genuinely is the truth. There are two completely different types of arguments that one uses to ensure this. And it's related to the nature of this continuity argument. So two cases depending on the relative sizes of m minus m tilde and r. So let me explain in words. We'll of course do this precisely, but let me explain in words. The first case is that these guys, m and m tilde, it corresponds to the case we had previously. These two are far away from each other. And I know at the previous step, g was close to that one. I make a small step. These two guys are far from each other, and therefore I cannot jump from the vicinity of one guy to the vicinity of the other guy. That's the philosophy in step 1, or case 1. So it's large compared, well, is large enough to use the previous step, and continuity. The second case is that this is quite small compared to that, and then you can't actually tell. You may when you enter this case, you may jump from the vicinity of this guy to the vicinity of that guy. But since this is small compared to that one, actually you don't care. You don't care whether you're close to this one or close to that one, because compared to the error term, they are both small anyway. So it makes no difference at all. So you can regard these two things as being roughly at the same point. Small. So whether to m, whether it's close to m or m tilde. Does this make sense? So this is the intuition. Is it okay? We'll try to do this precisely right now. Maybe just before I do that, I will define precisely where we transition from one case to the other. So the actual way of writing it is going to be a bit different, but if you recall from Lemma, what was it, 24 probably? Lemma 24, we saw that this thing is of order kappa plus eta. So instead of comparing r, this r here, I will compare to m minus m tilde, I will compare it to square root of kappa plus eta. And this r, I will use the bound that I will establish in this xi, which was delta k, in fact a square root of delta k, right? So I will compare compare square root of delta k with this, and that's going to be my threshold. So the crossover. So from case happens at, so this capital K, so this is the minimum. This is the minimal K such that delta K, so when this error delta K is in fact so you should take the square root on all sides, so square root of delta K is much bigger than square root of kappa plus eta, which you should read you should read this as square root of this as r being much bigger than n. Okay, so as long as, so this denotes the fact that you are in case 2, or let's say bigger than. This means that you are in case 2, so the transition, the crossover will take place as soon as you hit this behavior that characterizes case 2. It might happen that this never happens. In fact, if you are far away from the edges, then this never happens, and then the minimum is just equal to the maximal value of k, and you remain in case 1 all the time. That's quite possible. But sometimes you may hit case 2. One observation that's important. So as k increases, I want to make sure the following thing. I start off in case 1, right? So if eta is equal to 1, then the right-hand side is big. This is of order 1, and this is n to the minus 1/2. So this is clearly going to be wrong. So I'm in case 1. And I would like to make sure that eventually as k increases, I go down, I may reach such a threshold. And once I hit this minimum k, all subsequent k's also satisfy this condition. So if I once go to case 2, I never come back to case 1. There's no going back. That's important. You will see for the argument. That's very important. Otherwise, it would not work. So, and this is a simple monotonicity argument, which can be seen as follows. So as k increases, what happens to eta? Well, eta k decreases, right? That's by definition, eta k decreases. And therefore, delta k increases, right? Delta was a decreasing function of eta. So as k increases, delta k increases. And therefore, if you hit, there's a monotonicity in this condition, right? So if this condition is satisfied for some k, then it's also going to be satisfied for all larger k, right? Because this one only becomes the left-hand side only becomes larger, and the right-hand side only becomes smaller. So this is an important observation. We know that delta k so for all k strictly less than capital K, we have this bound. So we are in case 1, and delta k okay, so there's a monotonicity, and there's no going back. Let me draw a sketch of what's going on, which I think is very helpful, which you should really keep in mind throughout the proof. It really shows you what's the key idea of this whole argument and how these two cases behave. So I will draw a diagram in the following way. So I will draw eta on this axis here. So I have my 1, which is equal to eta 0. And then I will go down. So on the vertical axis, I have my eta. I will go down as k increases. And on the horizontal axis, I would like to draw the complex plane where all of these things take place. Right? So I would like to draw the complex plane of my g and my m and m tilde. So in principle, if I could draw this in 3D, this is something that you could draw in 3D, right? So I would have to draw a complex plane on the horizontal axis, but for the purposes of this illustration, I can just as well draw the complex plane as a line. I think that's fine. I will draw neighborhoods, complex neighborhoods as neighborhoods on this line. So what is the philosophy here? We saw, in fact, we just proved that if eta is equal to 1, then m and m tilde are far apart from each other, right? This one has a positive imaginary part, and this one has a negative imaginary part, and they are both separated away from 0. So these are far away from each other. And now as I start decreasing my eta, they will start to wander, and they can become very close. In fact, this typically happens if you are near the spectral edge. Go back to the definition of m and m tilde. If you are near the spectral edge, you will see that they are very close. In fact, we proved it, right? M minus m tilde was precisely of the order kappa, square root of kappa plus eta. Now, if you're at the edge, kappa is equal to 0. This distance between them behaves like square root of eta. Okay, so when you're at the very small scales, yeah, very small scales, this distance is going to be of the order 1 over square root of n. And now we have a neighborhood around every one of these guys. So we will establish, by solving the quadratic equation, we will establish that the g is in a certain neighborhood of size delta k around each one of these guys, and delta k increases as k increases. So I start off with a very small neighborhood, which becomes much larger. So this is the neighborhood around m, and then there's a corresponding neighborhood around m tilde. Okay, so let me draw, maybe I should have drawn these in slightly fatter lines. So this is my, so this is the actual value, and then this, okay, so this is m and m tilde, and I have a neighborhood of size square root of delta around each point. And this is how you see also very nicely how this continuity argument works. Maybe I should use some colors. So, I don't like colors usually because there's lots of technical issues. Maybe this is okay, so I'm using purple. So this the shaded region is the region where G is allowed to be. So I prove by solving this quadratic equation that G is close to either m or m tilde, and the error is precisely the width here of my tolerance. Now I know also, let me draw in green, let me draw G. So G is somewhere here. I proved in the previous lemma that when eta is equal to 1, G is close to m, not m tilde. Okay? By continuity, this is a continuous function in eta. So I cannot suddenly, this was the continuity argument, I cannot, if I'm in this neighborhood here, I cannot find myself somewhere around here, right, for a slightly smaller value of eta. Provided I make sufficiently small jumps, I cannot jump from here to there. So, because this has to be continuous. So my eta, my G can do something wild, but then as soon as I hit this region, I can do something crazy, and I can go even further. I can go to the extremes of this region of allowed values of G. And this would be case, so this is case 1. So this is case 1, and this is case 2. And you see, in case 1, these guys are sufficiently far separated that I actually have to worry that I'm here and not here. And I do that by continuity, because this guy cannot jump from over here to over there. And in case 2, I have no idea. These regions are mixed. I have no idea where I am, but the regions are sufficiently, these two guys are sufficiently close to each other that the distance between them is comparable to the width of my tolerance interval, and then I anyway don't care whether I'm here or here. It's just some constant 2 or 3 in my error. Okay, so this is the figure underlying my whole bootstrapping argument. Does this make sense? Is it clear to everyone? So the rest is now is going to be a formalization of what I explained here. So we have to treat these two cases separately. Now, let's see. So it's going to take me more than 15 minutes to finish this argument. And I think it would be nice to finish it in one go. So maybe, should we, since Johannes, you had more homework to discuss, should we stop here, and then you could take some more time for the exercise classes? Would this be a...
If you only need 5 minutes more, we can also...
Sorry?
If you only need 5 minutes more, you can also take 5 minutes.
I need 45 minutes more. So that I think that would be taxing the patience of everybody here. So maybe it's better if I don't start this argument, since it's clearer to do the argument in one sitting. I gave you the idea of what's coming. This is the basic idea. Now we just have to translate this into a more precise argument. We have all the notations, we have all the tools, we have all the estimates. So in principle, it should be smooth sailing. We will do that next time. But yeah, maybe now we can stop for here, and then Johannes, you can take a bit more time for the exercises, which is also helpful, because there were some exercises from last time that you were also discussing. So let's do that.
And we can start with the